Thank you for coming, and I want to really thank the organizers for inviting me to give this lecture, and I'm extremely sorry that I cannot be here to give it in person. The work I will present today has been led by Ye Wei, Zirong Peng, and Raiju Mosley. I will briefly touch on some work that Chiang Katnagao performed, and all of this with the support of the leadership groups, with Mark Tukubar and Andrew Breen, Michel Herbig, Eleni Maturahi, and Lee Stevenson. And all of this is performed in the departments of Dirk Haber and Jörg Neugebauer. We will first start with going back to some of the basics of how the atom probe works. If we consider an atom on the surface and we apply a high field, through the application of a high electrostatic potential, for example, the field can be sufficiently high that the atom on the surface starts to desorb and transform into an ion by losing some electrons. The ion in the electric field will be accelerated and be projected away from the surface. This combination of field-induced desorption and ionization is known as field evaporation, and this is the physical process that underpins atom probe tomography. In atom probe, we prepare the specimen as a very sharp needle with a radius of curvature at the apex below 100 nanometers, and we maintain the specimen at a very low temperature, usually below 80 Kelvin. We subject the specimen to a high voltage of a few kilovolts. At the apex of the needle, this high voltage translates into a high field, which is roughly the voltage divided by the radius, so a field in the range of 10 to the 10 volts per meter. If we again consider the surface atom under such high fields, they can transition into ions and fly away from the specimen, being projected normally from the initially normally from the surface. This gives rise to a very highly magnified projection of the ions onto a position-sensitive detector that will record the impact position of each ion. The field evaporation process is thermally activated and critically dependent on the strength of the electric field. So either by pulsing the field or by pulsing the temperature through the use of high voltage pulses or laser pulses, we can precisely know when the ion was created, and by measuring its time of flight onto the detector, we can identify the ion by time of flight mass spectrometry. By combining these two information, we can reconstruct the microstructure of the specimen in 3 dimensions. In that case, for example, it's a ground boundary in pure silicon that was decorated with carbon. The first information we get from an atom probe dataset is a mass spectrum, so we see a series of peaks. These peaks pertain to different isotopes or the different elements that constitute the material. And if we zoom in, for example, in this region, we can see chromium, vanadium, manganese, iron, all the isotopes one by one in this complex industrial steel that we were investigating at the time. To build the reconstruction, we're going to take every single ion impact and reverse project it onto a curved surface that is mimicking the specimen during the field evaporation process. So we are reverse projecting this position directly onto the virtual emitter. And every time we detect an ion and we process it, we assume that the next ion coming will come from a slightly lower position within the specimen. So we move down this virtual emitting surface by a small increment, and this depth increment is proportional to the size of the atom and inversely proportional to the detection efficiency, which is mostly related to the use of microchannel plates on the entry face of the particle detector, and is hence not proportional to the atomic weight of the atoms, but is a random loss of ions. And so we're going to keep processing ions one after the other until we've built the reconstruction in full. And in the end, we've built this 3-dimensional reconstruction, and every ion has a color which corresponds to its elemental nature. But the strength of the technique is really from being able to now look at species-specific 3-dimensional distribution. So for example, in this again, this same piece of steel, we can see a range of different maps to have different elements segregated at different places. So carbon inside a large carbide in the middle of the data set, some elongated features in the map of vanadium corresponding to segregation to dislocations, and we can see, for example, also a grain boundary where the carbide is sitting, where there's a slight segregation of silicon, for example, in that case, and carbon. So that's the strength of the technique. It's really in providing three-dimensional compositional mapping within complex materials. If we consider the full workflow of an atom probe analysis, we collect all of these signals on the detector, which are recorded digitally, and then we combine these first to mostly use the time of flight to build the mass-to-charge ratio spectrum, and then use the detector position, impact positions, to build this three-dimensional point cloud with some input from the mass-to-charge ratio spectrum. All of these actually require user input, and it means that they are prone to errors and mistakes, and it is really detrimental to the reliability and the repeatability of using atom probe for microstructural characterization. Amongst different things that user input is necessary for, we have, for example, the assignment of peaks to a specific element, the measurement of the composition, the deconvolution and decomposition of some of these peaks, where we have, for example, isobaric overlap or different molecular ions that are overlapping with specific other elements. And on the exploitation of the 3D point cloud, it's the identification of specific features, for example, how to report their composition, and potentially some aspects of the structural analysis. What we would like to do, and where machine learning has a big role to play, is to surprise this user input and automate some of these processes. The first example I'm going to show is to try and perform this structural analysis to calibrate the atom probe reconstruction. If we look back at the data, so I'm going to show you a sequence of detection of these ions. So these are just the position of the impact. And you can see a pattern forming, these rings, successive rings corresponding to the faceting of the specimen apex. And if I look at a two-dimensional histogram of these positions, I actually can see clearly some of the symmetries of the crystal appearing. There's also contrast corresponding to different phases that are present within this data set, and here you can see that the symmetries are broken right at the grain boundary, so we actually have twice the sample here from two different grains. Again, why are these patterns forming? If we look at the intersection of a curved surface with, in that case, a BCC crystal, and look at exactly what is happening right at the apex, the formation of these terraces will lead to slight changes in the electric field. So locally, the atom here at the edge has slightly less electrons, is less bonded with its neighbors, so the field is locally higher. And this will induce aberrations in the trajectory of the ions. So instead of flying straight, the ion might actually have a slightly different trajectory right at the edges of these terraces. So we end up with non-homogeneous detector maps, and these inhomogeneities reflects the symmetries of the crystal. Each one of these local changes in density can be related to a specific crystallographic set of crystallographic planes, and the pattern is specific to the structure and the orientation of the specimen. This can be very useful in the case of nanocrystalline samples, for example, where we can see, in that case, segregation of different species to the grain boundaries that are formed. And by looking at the detector map, we can deduce what is the local orientation of each of the grains that we are imaging within the data. In the case here, for example, of a hydride, titanium hydride that has formed at the previous grain boundary between two alpha grains, alpha titanium, if we look at the detector map in the top and the bottom, we can see a six-fold symmetry that is characteristic of the 002 planes of the HCP alpha matrix. And in the middle, where the hydrogen composition is high, we see a different pattern forming with a typical threefold symmetry from the 111 set of planes. The superimposition of the poles between the bottom grain and the 111 pole of the FCC titanium hydride is an indication of the orientation relationship between the two phases. So we can do atom probe crystallography. Effectively, as I said, it can be useful when we have multiple grains to deduce the orientation of the grains with respect to each other. But also one issue that we face and where user input becomes a problem is if we look at the set of parameters that we need to build a reconstruction in atom probe, and if we can play around with them, we end up with microstructures that are completely different. And there are ways and methods that have been developed over the past 10, 15 years to constrain the reconstruction and deduce what are the right parameters to use. But this requires indexing of the crystallographic planes and pattern, and this is usually a slow process, and it's prone to errors because we need basically user expertise. And so what we wanted to do was to automate this detection and the identification of the poles. And so this is what Ye and Andrew started doing. So if we look at these types of maps, we can associate to each of these poles that we see a specific set of planes, in that case 111 and 220, for example. And the good thing for us is that if we want to index these maps automatically, we are dealing with a system that is actually well constrained. So we know that the total field of view of the atom probe is roughly about 60 degrees. Most of these maps coming from, in that case, pure aluminium, FCC pure aluminium, will contain one of the major crystallographic directions, so 100 or 111 or 110. And because of the symmetries of the crystal, there are fixed angles between different poles because they correspond to different sets of planes. So this is something that we can actually make use of. And what we really want to have is a way to go from having a map through some sort of machine, which is very often a black box, to a map that has been fully identified, where poles have been fully identified and associated to a specific crystallographic direction. But we don't want to do this once, we want to do this many times, and even maybe more times than you can think of. So what we used to our advantage is the fact that, again, we have these constraints in the system where we know if we can find 4 poles and identify them, there should be known relationships between the angles that are formed within triangles that go from one pole to the other. And if we look at the relationships, experimental relationship between some of these sets of angles, they are very, very, very close to being what the theory dictates. So we could actually make use of this information again. To make the most of these relationships, what we did was take a series of experimentally characterized maps and move the poles around a little bit to generate a vast amount of different configurations, about 60,000 of them. And then look for ways to perform dimensionality reduction, which is now classified as machine learning, but it's basically principal component analysis done in a specific way. And PCA has been used in the field of microscopy for quite a long time to process spectra especially. And so we did use this T-distributed stochastic neighbor embedding, TSNE, which is a very common method akin to PCA, once again, to look at the data in a specific way. And this allowed us to easily cluster the different configurations of poles. And there are a few outliers, but mostly it means that if we reduce the dimensionality of the data in this specific way, then we can fairly easily distinguish the different sets of poles that we have within the map. And then we need to associate a map to an orientation. So the way to do this has been to follow, first train a machine, so define what the machine should be. And so for this, we first detected the poles through image processing. And then we define a series of functions, the machine. And what we were doing was input these pole positions into the machine, given a series of weights, and recombine the output of these functions with a different set of weights to find an output, and the output being a possible orientation. So associating a pole to a specific set of planes or direction. And then compare this to one of the known maps that we had through this library of pole positions that we had generated. And if there was no match, then feed this back through a loss function into a new set of weights calculated and get a new output. And this we can do, again, compare to the non-identification, and do this again and again and again with a progressive improvement in the possible match by calculating this loss function properly. And at the end, when we end up with a match, then we can assume that the machine's been well trained, and we do this for multiple cases, and at the end of the day we are happy with the way the machine works. So this is a bit more complicated, but the concept is the same. So what we used was a deep neural network with 5 different layers, and the function that we used in that case was a rectifier linear unit. And what we were doing was basically inputting all of these different angles, going through all of these functions with these weights that we have assigned, up until the point where we could match the orientation as an input to the orientation that we had as an output. The training time with the library that we had was about 3 minutes. We then looked at how this new neural network was performing, and we can see that it tends to get very accurate quite quickly after just a few iterations, maybe less than 20, for the training and the test that we performed. And we could see that in almost all cases where we had predicted a certain label, it was actually falling into the real class during the training. So the machine seems to perform really well. We also looked for cases where it wasn't working that well, because the map wasn't very clear, or because in some cases you can see here for some specimen, for example, where the analysis conditions are not optimal, then we can see that some of the poles are disappearing, so we can't really identify them anymore. Or in the other case, we are basically lowering the field of view progressively, and at some stage there's not enough poles to perform the technique. But for most of the data sets that we used in that case, we ended up with an identification that after checking seemed to be fine. And we could identify 400 maps within just a few seconds. So this work was published about a year ago. It was just a first attempt, and it seems to be quite successful. And so we are working now on the next steps to use this pole information to constrain the reconstruction, for example, combined with Fourier transform or spatial distribution maps to determine the interspacing, and all of this leading to an automated calibration of the reconstruction. Let's now look at a second example of where we try to remove user input, which is to extract compositional information from specific features. So let's look at a nanocrystalline thin film, for example, of metal on top of tungsten carbide, which was used as a coating for precision glass molding. And we can see in the TM image here, for example, clearly the trace of a grain boundary, with likely some chromium segregation at this grain boundary based on the EDX results. And the atom probe analysis from this very similar region, we can see compositional variations there are, but identifying precisely what the grain boundaries can be quite challenging. So typically the way we do this would be to put a series of regions of interest locally, or looking through the data at some of this segregation of chromium, for example, in that case. And whether we can actually automatically identify some of these features would be extremely valuable, because for now, placing all of these regions of interest manually is not only tedious, it's also prone to errors. We decided to work on a slightly different material then. It's a nanocrystalline nickel, so also a metallic thin film that has been deposited, so columnar grains, and then we perform a lift out, flip the sample, look through the specimen that you can see here. We can see through a precession electron diffraction that there are many, many grains within the specimen, and we can actually go down to measuring the misorientation between the grains, and then we try to correlate this with the compositional map that we get from the atom probe, and potentially get to the point where we can derive the interfacial excess. So what we wanted to do in that case is actually, again, use machine learning to determine where these different grain boundaries would be. So we use tools that are typically used for molecular dynamics simulations to set up a number of cells containing grains and grain boundaries. And there is a record of where the grain boundaries are and where the grains are. And you can see here in this map, for example, at the top, you can see that the white atoms correspond to atoms from the grain boundary, the green ones from within the grains. And so we can actually play around with these, the misorientation between the grains and so on and so forth. And then what we can do is actually look at the way that the map, the structure changes by looking at where these atoms are sitting. And then we can actually associate to some of the atoms at the grain boundary or within the grains a different local composition. And what we end up with, if we smear out these positions a little bit, so it would look a bit more like a proper atom probe dataset, is an image of the projected image of the compositional field. And what we could do afterwards is just simply divide these images into a vast number of them, smaller but a vast number of them. Thing is, in all of these, we actually know whether atoms are grain boundary atoms, grain atoms, or potentially even triple junction atoms. So we can classify all of these different types of images as being inside grains, grain boundaries, or triple junctions. This is actually quite useful because we don't need a ton of experimental data in the first place. We can just use some of these simulations. We can make many more of those. It takes time, but it takes less time as looking at experimental data. And what we did afterwards was test this an approach called TensorFlow, which is a neural network-based approach that's been developed by Google, which is freely available and fairly easy to implement. And then we looked at whether the TensorFlow could actually use this library of different images that we've generated for the different structures to classify them properly. And in most cases it works. We have almost 90% success rate. And it means that then if we look at a compositional map from an atom probe dataset projected along one axis, we might be able to use this to directly distinguish whether a local part of the microstructure is a grain boundary or inside a grain, or maybe a triple junction. So we looked at these, the results from this application of this TensorFlow protocol, and this is one of these nanocrystalline nickel datasets, and you can see that it's detected a whole network of what could be grain boundaries, and we could actually determine locally where these grain boundaries could sit. And these are the green lines in the map. And then if we look just at the triple junctions and then join the triple junctions together, we get a result that is probably even more accurate with respect to where these grain boundaries are sitting. So then we look back at some of the approaches that Zhirong Peng had developed for mapping compositional variations within a grain boundary. And in that case, we start with atoms that are sitting at a grain boundary that have been extracted from the data in the first place. Then through principal component analysis, we look at the way the grain boundary is oriented. And afterwards, within every single one of these little voxels that we've defined, we move the position of the interfacial regions that we've just defined to where we find the highest number of atoms. This gives us an idea of where the grain boundary plane is sitting with respect to the point cloud, or the section of the point cloud. And then we also helps us define the local normal to the grain boundary, so then we can look at the profile along this normal and associate all of the atoms within the dataset to a specific voxel and calculate locally what is the composition. So we calculated all of the composition profiles from all of these different sections of the boundary that had been defined. And you can see it fluctuates quite a lot in that case. And then we can calculate the also the cumulative composition profile, which gives us an idea of the local interfacial excess. And so we also developed a full protocol to directly derive the local excess based on a fit of the three sections of the profile. So the composition inside the first grain, inside the second grain, which can sometimes be a bit different, and right at the interfacial region, what is the jump in between these two? And that allows us to determine the number of atoms that are in excess at the boundary. And so based on this, we can actually directly input the points that we had generated from this analysis of where the ground boundary is sitting, and we can actually directly determine the local composition and the local excess of phosphorus, in that case at the ground boundaries in the nickel, nanocrystalline nickel. So I'm getting close to the end, right? So it's just a very partial view. So I just wanted to thank you for your attention again, and want to thank all of the wonderful funding agencies that give us money and that allow us to do some of this great work that we're doing. Thanks for your attention. And if you have any questions, please shoot them and I'll reply to them as soon as I can. Bye. But I hope it was quite interesting to you. It's mostly work in progress. We've done quite a few steps, but there's many more to come. So we looked at automating the local compositional measurements. We looked at trying to find ways to constrain the reconstruction and calibrate the reconstruction through input from electron microscopy. We looked at also ways to maybe use machine learning type approaches to derive on field and microscopy data to directly map where the atoms are sitting with respect to the specimen surface, allowing us to progressively build three-dimensional reconstructions with true atomic resolution, but no elemental identity yet. And we also have some more mapping tools for different microstructural features and ground boundaries that we've submitted for publication. There's been work by other groups, obviously. So the group at Oxford did quite some awesome work on cluster identification through machine learning, for example. So we're not the only group interested in this. And again, if I get back to my initial graph, there are many other aspects that would benefit from removing user input to make things better. For example, the peak assignment or measurement of the composition or decomposition of the peaks. So we are pushing a bit in this direction, for example. So you have these very complex mass spectra, and we managed to associate to all of these peaks an identity that is not completely meaningless. So there's a lot of work that needs to be done, but it's getting there.